Live from Earth, it's Space Radio. This is Paul Sutter, and coming up, we're talking about, it's a black hole, told you so. And of course, taking listener questions about all things in the universe. We record the show every Thursday at 4 p.m. Eastern, so you can leave a voicemail on our website. That's spaceradioshow.com. You can leave a voicemail anytime, day or night, and you can get your voice on the air. And in today's Blue Shift, I'll be talking about the mystery of interferometry. But first, the news. Hello, space fans. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Ohio State, and for the next half hour, your agent of the stars. Got an exciting show for you today on Space Radio, where we talk about all the amazing, beautiful, wonderful, and sometimes mysterious things in this universe. This show lives on listener questions. We record every Thursday at 4 p.m. Eastern, so leave a voicemail on our website. Go to spaceradioshow.com. Get those questions in and I will play them on the air. You can also follow along on our live streams every Thursday at 4 p.m. Eastern. Those are over on YouTube and Twitch, and you can follow along with our space cadets tuning in live from around the world, including but not limited to Pittsburgh, Pennsylvania, Stavanger, Norway, Ashburton, New Zealand, Calgary, Alberta, Stockholm, Sweden, Vipava, Slovenia, London, UK, and Halifax, England, and more. For the links to the live streams, go to spaceradioshow.com. How handy is that? It's the same website for everything. We'll take questions from the space cadets too. Of course, seriously, folks, I've only prepped 10 minutes of show material, tops mostly less than that, so get those calls in. Hey folks, how's it going? Before I start taking questions, though, I want to share the big news of the week. Now, everybody's talking about it, so of course, I'm going to talk about it. Usually I just let other people do it and I go off in some other direction, but I can't help it because it's a giant black hole and we have a picture of it. That's the image that has splashed all over the internet, all over the news. Everyone's talking about. Congratulations to the Event Horizon Telescope team. Man, they have been working on this for 2 years. 2 years. And by working on it, I mean they finished getting the data 2 years ago. And they've been working for the past 2 years of just trying to produce this image from the data. That's not even including all the hard work of actually, designing this instrument, figuring it all out, planning it, actually doing it, collecting the data. No, this is just 2 years of just grinding in front of a computer, trying to make sense of it all so you get a pretty picture. And what a pretty picture it is. This is an image of the black hole in the center of M87, which is a big old galaxy about 55 million light years away from Earth. And last week I called it. I told you exactly what it looked like. And, I'm not tooting my own horn here, but here I am tooting my own horn. That it's a fuzzy, bright thing, orangish, whitish, with a hole in the middle. Congratulations, that's what a black hole looks like. So what you're actually seeing in this image is the ring of material around the black hole, something we call the accretion disk. This is stuff falling into the black hole, and as it falls in, it rotates really fast and compresses and presses and heats up. And then there's the black hole itself in the center that looks like a little cutout, looks like a little donut hole in the middle. That is where material actually crosses the event horizon. Light cannot escape, and we have the black hole. Now, this accretion disk is brighter on one end than the other. This is due to a very, very cool effect called, are you ready for this? Relativistic beaming, where this disk of material that's swirling around that black hole, it's going so fast that the material that's on one side that's flowing in our direction, because it's going so fast, because it's going close enough to the speed of light, it can take its radiation that it emits in all direction and beam it. It can focus it forward towards us. So we get like a bright light coming off that side of the disk that's swirling towards us, and then the side that's swirling away from us looks a lot dimmer. That's why there's that nice bright bulge right in the center. The actual black hole, we got pretty lucky with this image because the accretion disk in the black hole could have had any orientation. It could have pointing towards us or away from us or sideways, profile, whatever. We got pretty lucky. We're looking almost nearly top down on it. It's off by about 20 degrees or so. So we get the full accretion disk all the way around it. But because of that tilt, some of the disk is pointed towards us a little bit. That's what gives us that relativistic beaming effect. And we get to see the hole cut out. Now, this is a monster black hole. If you put it in our own solar system, it would go out to like the orbit of Pluto or something, the event horizon. That's a big thing. What a pretty picture. We're not learning too much from this image. I mean, it's consistent with what we expect from general relativity, yay, which is nice. You know, it would have been nice for it to be weird, but, you know, we'll take what we can get. We're not learning too much from this observation, but follow-on observations now that they know what they're doing, get higher resolution, get better, more black holes, we might start to learn some really, really cool stuff. And of course, that is the latest and greatest when it comes to the news, but it's time to have a conversation. Space cadets. Larry, weird and proud. I'll go ahead and ask this. I can just turn this all into the Event Horizon Telescope image questions. Yeah, you guys are already asking lots of questions about it, so I think I'll just do that. Do I enjoy cuddling? Glenn, wow. I know it may not look like it. I know Nancy deleted the message, the question. Glenn Matthews asked if I enjoy cuddling. Yeah, I love cuddling. I'm a cuddler. I'm not going to deny it. Okay, so we've got questions from Gordon Lee, questions from Peppers, and Astro B. So I'll try to get those three in this segment. Great questions about the black hole. We've got questions piling in from the space cadets all about this image of M87, the giant black hole from the Event Horizon Telescope. And so I'm just going to get right to it with these questions, starting with Gordon Lee asking if this black hole is 55 million light years away from us. We're seeing it as it was, but as now, could that black hole be gone? Or do you think it's still there? Like, what's going on? That's right. So this thing is 55 million light years away, which means it took 55 million years for that light to reach us. So the light, the picture that we have now, like the picture that's being circulated everywhere around the world right now, that light was released shortly after the dinosaurs bit the dust from the Great Impact. That's how long this light has been traveling. And so it's reasonable to ask, what's there right now? Like, is it the black hole destroyed? Has it wandered away? Is it bigger? So as far as we know, of course we can't know because we only have the data that we have right now. We'll have to wait another 55 million years to see what happens, what's happening now. But the light from this black hole is telling us that this black hole is actually relatively stable. Black holes, especially giant ones, really do hang around for a very, very long time. They like to settle and nestle into the hearts of their galaxies, and they'll just take up shop. They'll squat. They're not paying rent. They're just hanging out, minding their own business, doing their own thing. So, and also this image of the black hole, the accretion disk was pretty stable. It wasn't flaring up a lot. It wasn't varying a lot with time. So as far as we can tell, if I had to guess, and that's the only thing I can do, right now, that black hole in M87 is still there. Got another question here from the Space Cadets from Peppers over on YouTube. When can we expect to see a picture of our own black hole? That's right. Every galaxy as far as we can tell, hosts a supermassive black hole in its core, including the Milky Ways. And now this is something I did get wrong last week. Last week, I thought for sure this was going to be an image of our own black hole, something we call Sagittarius A star. And it's not. It's not. Instead, it's an image of M87. They're still working on the image of our own black hole. There are two problems that they're trying to overcome with our own black hole. One, because it's inside of our own galaxy, we have to look through our galaxy to get a picture of that black hole. And there's a bunch of junk in our galaxy. Dust and gas, like it's just glowing, doing their own things, being annoying. It's like trying to look through a crowded room at someone at the other end. Whereas M87 was, yes, it's further away, but it's outside the plane of our galaxy, so that you have to look through a lot less junk. It's like looking through an empty room at someone at the opposite side. So there's a lot of dust that they have to contend with in order to make that clean image. And also, our black hole, as far as we can tell, because we've seen flare-ups from the region of the black hole, changes over the course of a few hours and a few days. Like the brightness of that accretion disk is constantly changing. And they have to take a lot of data over the course of a lot of days and average it all together in order to build up this image, like taking a long exposure photograph. And since the accretion disk around our own black hole is changing so rapidly, it changes over the course of an observing run. Like while they're taking the picture, it's changing. And so that makes it hard to do the analysis, to make the averaging, to get like a solid picture of it. Whereas M87, the one that they did release, is much quieter, much more sedate. It stayed stable over the course of multiple days. And they actually have this in the paper. They have like, here's day 1, day 2, day 3, day 4, and it's like the exact same picture every time. And so they can take all that data from multiple days of exposures and crunch them down into the same image to get that nice picture that they release. So they are hoping to release, the Event Horizon Telescope team is hoping to release an image of Sagittarius A star, our own black hole, sometime soon. And that's academic speak for sometime in the next 3 years. It's gonna be soon, but who knows how soon. Astro B following up, and I'll start this question, then I'll have to take a break, but then I'll keep going with the answer to this question. Astro B, one of the space cadets, is asking, so what do we know now about M87 now that we have the computer-generated images with the false color? So one of the great things that the team did, and what the team has been doing in the past few years and other collaborators have been doing, is predicting what these black holes might look like. And that's as far as I can get before I go to the break. But before I go, this is Space Radio. I'm Paul Sutter, and this show is brought to you by you. That's right. No, not you. You. Go to patreon.com/PM Sutter to learn how you, not you, but you, very specifically you, can help support the show. Seriously, $5 a month, $10 a month, $100 a month. Some small contribution is exactly how this show stays on. And I will see you after the break. Great question, Space Cadets. Love all these. So Astro B, I'll finish answering your question. Larry Weird and Proud, I'll do your question. And JD40CEK, I'll get to yours. Gordon McGlennon, I'll do yours. Incognito, I'll do yours. Gordon, I'll do yours again. So many questions. Oh, that's right. Davis Curtis, Roy Kerr. I've met Roy Kerr. Super cool guy. I was at a conference in New Zealand. I got to meet him once. And he's all like, hey, I'm Roy Kerr. And everyone's like, oh, it's Roy Kerr. You have things named after you. Ooh, and Tommy Vask, that's what I'll talk about in the Blue Shift, about the synchronization between the telescopes. Yeah, and it also helped when it comes to MA7. MA7 is 1,000 times further away than our black hole, but it's about 1,000 times bigger. So it kind of canceled each other out. And it just turned out to be an easier target. You guys ready to rock for the next segment? No? Okay. I can keep waiting. We're all space cadets. That's right, Nancy. Bob, you're a space cadet. Welcome to the Academy. Borat, I just answered that. Yep, Sagittarius A-star picture is coming. They're still working on it. Don't hold your breath. It'll be like months to like a year before they get it out. But it's coming. It's coming. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio, and it is a bonanza about the Event Horizon Telescope releasing the image, the first ever image of a black hole at M87, a galaxy sitting 55 million light years away from Earth. Before the break, I was answering one of the Space Cadet questions, Astro B, saying, what do we know now about the black hole? Because, yeah, we have the image, but like, how do we actually know things about it? And we know things about it because we understand general relativity, which is our picture of gravity and how we know black holes exist. And we know the astrophysics, to some degree, of how the material around a black hole swirls in and compresses and makes a disk and then eventually falls in. And so we can perform computer simulations of this. We can run all the physics and put the pieces together. We can predict what the light will look like coming off of this accretion disk and before it falls into the black hole. And we can even simulate how the Event Horizon Telescope itself will collect this data and run it through all their analysis and run it through all their machinery to generate the picture so we can generate simulated telescope observations. This is something that's done all across astronomy. And this is how we learn, by like matching it. Like, okay, so we got this image. Let's look in our simulation box and which one was closest. Aha, this is the closest with this big of a black hole, with this kind of orientation, with rotating at this spin rate. That's the one that most closely matches the image we actually got. So it's about comparing. It's about comparing, and that's how we know about the mass of the black hole, its spin rate, its orientation, the amount of material in the accretion disk, all that. Now, continuing on, Larry Weird and Proud, hey, if you're going to be weird, you might as well be proud about it, asking how much time did it take to actually collect the light for a single image? Now, I don't know this number off the top of my head. I believe it was 4 to 5 full days of observations of nonstop data collecting. And it was a lot of data. It's something like 5 petabytes of data collected. And if you don't know what a petabyte is, don't worry about it. It's just a lot. It's like way more than what's in your computer hard drive. It was so much data that they couldn't actually transport the data through the internet because that would have taken forever. They actually had to use physical hard drives, like each telescope that was involved in this network of telescopes around the world, collected data, stored it locally on a hard drive, and then they had to like drive out and pick up the hard drive and drive it back to the lab. And that's how they collected the data. It was a few days worth of observing for each run, and I think they did multiple runs. JD40CEK over on Twitch is asking, can you elaborate on the difference between the event horizon and the shadow of the black hole? So yeah, that hole cut out in the image that you're seeing, that's not the actual event horizon. That's not the actual boundary of the black hole. Instead, it's something we call the shadow of the black hole. The event horizon is actually smaller, but because we're looking at this thing from an angle, there's going to be a region of the accretion disk that is not going to light up simply because the black hole is going to cover more of it because of its orientation. Plus, surrounding the black hole, because it's spinning, is something we call, this is one of my favorite words, the ergosphere. And the ergosphere is where space-time itself is rotating around the black hole. And obviously not a lot of light is going to come from that region. So it's these kinds of geometry effects and space-time curvature and rotation effects give us this region called the shadow. And moving on, Gordon McLennan asking how far away from the event horizon is the accretion disk? We're talking millions, billions of miles away. Like if you were to plop this thing down in our solar system, the event horizon stretches to something like Neptune or Pluto. It's pretty far out. And the inner edge of the accretion disk is somewhere like in our Oort cloud. It's millions, it's billions of kilometers or miles away. Pick the unit of your choice. There's a wide gap between that bright inner edge of the accretion disk and the event horizon itself. Obviously, material, it's not empty there. Material is falling into the black hole actively. It's just not lighting up enough for us to see it. Incognito over on YouTube is asking, how do they tell the age of the black hole? Now, the age is a little bit tricky because we can get the mass, we can get the spin, we can get the orientation. The age is more of an estimate based on its mass and the mass of its host galaxy. And because galaxies host black holes like this, and they're tied, the growth of a galaxy is tied to the growth of a black hole, we can kind of sort of peg the age of like, okay, if we look at a certain galaxy and it's a certain type and has a certain star formation rate, you can kind of sort of guess at the age of the galaxy. And galaxies co-evolve with their parasitic hosts or parasites, the black holes. And so you can kind of put a rough estimate on the age of the black hole. Gordon McLennan back again over on YouTube is asking, could these images eventually prove Hawking radiation? So Hawking radiation, developed by Stephen Hawking, who unfortunately passed away just a year ago and didn't get to see these images for himself, predicted that black holes aren't 100% black. They do glow a little bit. They do emit radiation, they do emit light, but they do it very, very, very slowly. For a black hole this size of something like M87, we're talking about one photon a century. Like the entire black hole through Hawking radiation is emitting one photon every century. That's pretty slow. So with images like this, we're not going to get a picture of Hawking radiation, but we might be able to get some indirect evidence of what's going on in the event horizon or near the event horizon because we are directly imaging it. Like we are looking at the event horizon and its shadow and the accretion disk and the environment directly, like right up against a black hole. So if you have some crazy theory, some crazy model of what's going on at the event horizon, it might affect, say, the ergosphere. It might affect the shadow region. It might affect how the accretion disk behaves. And if you can find a way to test your theory by looking at pictures like this, well then, step up to the plate and let's see what you got. Speaking of rotation, Dave Curtis asking over on YouTube, can you explain Kerr geometry of a spinning black hole? Roy Kerr is the astrophysicist who figured out mathematically how black holes spin, and this is a spinning black hole. And so when black holes spin, they get fatter around the middle. And like I said just a little bit ago, they can pull space-time with them. Like if you've got a coffee table in the middle of a rug and you twist the coffee table, it twists the rug with it. That's kind of sort of what's going on. So it's actually dragging space-time around the vicinity of the black hole, which is so intense. And unfortunately, we're almost out of time today. But before we go, it's time for the blue shift. Wow, non-stop questions. I'll just keep going. Well, I know I wanted to talk about interferometry. Oh man, so many good questions. So many questions. I'll probably stay longer after we're done with the show. Keep hitting up these questions. These are really, really good questions. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get just a little bit closer to you. And I wanted to talk about the magic of interferometry, but then I got this great question from Tommy Vask, one of the space cadets, asking, can you tell us more in depth about how the synchronization of the telescopes was achieved? So I just want to dig right into that, which is what I was going to talk about anyway. And it just so happens to be a question. Now, the Event Horizon Telescope isn't just one telescope. It's a network of telescopes all around the world. Individual ones, like one on every continent, all collecting data at the same time. So what they're doing is each instrument, each antenna, each observatory is taking their picture of the black hole. They're staring at the black hole in the same region of space at the same region of time. And then you take all the data from all the individual telescopes, make sure they're all lined up, they're all synchronized so that, okay, when this telescope was taking data at this time, it matches with what this telescope over here on the other side of the world when it was taking its observations. And you very, very carefully stitch these images together in a process that we call interferometry. And there are pluses and minuses to this process of interferometry. When you build a telescope, any telescope, you want two things. You want it to be big, because the bigger, the wider your telescope, the smaller the thing you can see in space. And these black holes are very, very tiny in the sky. And you also want a lot of collecting area. You want a big bucket to collect a lot of light. You want to take a big picture. So with an interferometer, because these individual elements were on opposite sides of the Earth, it's as if you had a telescope as wide as the Earth. But there's a downside. It's not quite a telescope as big as the Earth, because a lot of the light coming from M87 from these black holes doesn't hit the antenna where it's useful. It just hits dirt in oceans and people's roofs. It's some of that light from M87 is hitting your face right now, but it's not useful. You're not collecting it. So it's a telescope as wide as the Earth, but you give up a lot. You have to take a lot of data. You have to run these observations for a very long time to make up for those gaps between your telescopes. And you very carefully put these images together in that process called interferometry, and that's exactly how they did it. And unfortunately, this broadcast is almost done. Thank you for joining me on this very special supermassive black hole edition of Space Radio. Once again, I'm Paul Sutter, and this show is brought to you by the Ohio State University Department of Astronomy. Learn more at astronomy.osu.edu. This show is also brought to you by, that's right, you. Go to patreon.com/PM. Sorry, I can't emphasize it enough of how your contributions, you keep this show going. It's all up to you. And if you think, oh, someone else is going to take care of it, you're wrong. It's up to you. Thanks to Greg Moebius for producing, Nancy Graziano for wrangling the Space Cadets, Dan Mashalko for being awesome, and all the fine crew at WCBE Radio for making this show possible. We record every Thursday at 4 p.m. Eastern. You can leave a voicemail on our website, that's spaceradioshow.com, and there you can also find links to our live streams, show notes, episode archives, more about me. You can buy my book if you wanted to, Your Place in the Universe, Understanding Our Big Messy Existence. And of course, thanks again, Earthlings, for listening. See you next week, and remember, science is for sharing. End of transmission. But don't worry, Space Cadets, I'm not abandoning you yet. I'll abandon you later, when you deserve it. You don't deserve it yet. I'm here for you right now, but in a little while, I'll abandon you, so you just prepare yourself. Would Gordon Lee, would the James Webb be able to take a clearer picture of the black hole? No, actually, the James Webb's going to suck at taking pictures of black holes. This, like, because the James Webb mirror is big, right? It's giant. It's like folding out. It's like 15 meters across or something. This telescope was the width of the entire planet Earth. So if the James Webb primary mirror was the size of the planet Earth, it'd be pretty fantastic at taking pictures of black holes. But the Event Horizon Telescope has got it beat. Guillaume asking, why is there a jet coming out of a black hole? So the jets don't really come from the black hole itself. Once you fall into a black hole, you're done. Kaput. It's over. But the accretion disk itself, as it's swirling and circulating around that black hole, has extremely strong electric and magnetic fields. And these extremely strong electric and magnetic fields can whip up and corkscrew around the surface of the black hole and then eventually wind up to form a jet and blast this jet off into space. And that is the origin of the jet. It's actually coming from the accretion disk rather than the black hole. And a little bit of a buried lead here of this Event Horizon Telescope release. We're not, especially from this first image, we're not going to learn a lot about general relativity. Like, we're not going to learn so much about black holes. We are going to learn a lot about accretion disks, though. We're going to learn a lot more about the astrophysics of these systems rather than the general relativity gravity of these systems, because that's what we're actually taking a picture of, is the accretion disk itself. So now we can actually see how an accretion disk behaves around a black hole, which is going to pay dividends when it comes to understanding these jet accretion systems. Bob is asking, does a black hole have a physical surface? No, there's no physical surface. The event horizon is just an invisible boundary in space. In fact, for these giant black holes, you don't even know when you fall in. Slinker Deer is asking, could there theoretically be a habitable zone around a black hole accretion disk due to the heat and light produces? That's going to be a tough one because these accretion disks are emitting very high energy radiation. Like the Event Horizon Telescope image, this is up in the ultraviolet, I think. Like, that's high energy stuff. And you basically don't want to be anywhere near. There's no safe distance around an ultraviolet emitter. I mean, maybe if you worked hard enough, you could figure something out, but I'm not betting on it. I'm betting on it. Chris Tolson, what can this discovery lead to? I think it's going to lead to, especially this image in the image of Sagittarius A star, is going to lead to a lot more knowledge of astrophysics. If you were to orbit it, man, you would just, if you're on a planet orbiting this system, keep in mind you'd have to be like a light year or multiple light years away from this whole system to be able to be orbiting it or to see it as one thing. And it's basically what you see in this image, except bright visible light, and it would melt your face off, which is kind of a problem. So you might want to wear some sunglasses. And it's going to be what this image is. It's going to be what this image is. Are we seeing the jets in the MA7 image? No, we don't get a clear picture of the jets because it's pretty face on to us. So the jet's coming off just at a little angle like here. And the jets really extend out. Like, those things go thousands of light years. So when you zoom out, we know the jets are there, but we're like way in on it. So we're not going to see the jets. Orson Zed is asking, could Sagittarius A star not have been our original black hole? Sometimes black holes eject. So there's a relationship between size of a galaxy and size of a black hole. That relationship isn't perfectly matched. So there's going to be a lot of variation. And we'll see. We'll see. I'm pretty sure, like, Sagittarius A star is the black hole that we grew up with. I don't think there's any evidence, as far as we can tell, that we ejected our black hole or our black hole was replaced. I think this is the one we got. Bob asking, does a black hole have an inside? Yes, if you're past the event horizon, you are within the boundary of the black hole. Supermassive black hole, great name, is asking any chance we could soon image a small black hole from a supernova. That's going to be a lot tougher. So these supermassive black holes really are big. Like, they're bigger than a solar system. A supermassive black hole is the size of like a city, or not A stellar mass black hole, like one from a supernova, that's the size of a city block. So the nearest one is thousands of light years away, and it's just the numbers don't really work out. You'd have to start putting part of these interferometer instruments out in space in order to be able to see it. Can the event horizon take a picture like the Hubble Ultra Deep Field? Yeah, they could. It'll be an ultraviolet, and I don't think you're going to see you don't see a lot of galaxies in ultraviolet, especially deep galaxies, but it can take pictures of black holes. How come the matter, so Tadesh is asking, how come the matter doesn't fall in the black hole faster since the gravity is so strong? It does, man. That stuff swirls in like crazy, like close to the speed of light. That's how we're getting this relativistic beaming effect. Mike McCall is asking, how did they know there was a black hole there? So we knew there was an accretion disk there. We knew there was a bright blobby thing. We just didn't have a good picture of it. And we knew of the jets coming off. And so we had figured that there's going to be a black hole there. These are the originators of these massive accretion and jet systems. So we had a really, really good guess that there was going to be a black hole in the center there. And we were right. Tommy is asking, might neutrinos be able to pass through a black hole? Nope. Neutrinos, sorry. Nothing. When I say nothing, I mean it, mister. Gordon Lee, what if those jets hit a planet in another solar system light years away? So they do. The jets sometimes actually face us, but they're coming from tens or hundreds of millions of light years away. And when we do, we call those blazars. So if you ever heard of a blazar, that's when one of these jets is pointing right at us. If you're close, you're toast. Good thing it's millions or billions of light years away. Scott is asking, what is the smallest black hole possible? The smallest black hole possible that we know of is when the event horizon is the size of the Planck length. And then you're starting to get into this weird boundary between general relativity and quantum mechanics, and like who knows what you're gonna get. So we'll just put the cutoff there and leave it at that. All right, you guys are starting to wind down. Thank you so much for watching. This was a very cool episode to do. It blew by. I loved how all the questions were about the Event Horizon Telescope. And I will see you next week for more fun adventures. Take it easy.